So, because solubility can be considered as an application of equilibrium, we can also analyze the factors that would affect that solubility equilibrium. All of these factors that we're going to discuss are really applications of Le Chatelier's principle because solubility is an equilibrium process. And so the ones that in particular come up are the idea of the addition of common ions, the changing the pH of the solution, and the formation of complex ions. So, first, consider a beaker that contains 100 milliliter of water with solid silver bromide on the bottom of the beaker, meaning that the solution is saturated. What will happen if more silver bromide solid is added? The amount of silver ion in solution will stay the same because remember, solids aren't in the KSP expression, so adding more solid to a saturated solution won't change the equilibrium concentration. Okay, let's consider that same 100 milliliter beaker with solid silver bromide on the bottom. If we add instead sodium bromide, how will that change the amount of silver bromide and also the concentration of silver plus ions? So the amount of silver bromide will increase and the concentration of silver plus ion in solution will decrease. So let's think about that. The KSP expression for silver bromide is AgBr solid becomes Ag plus bromide. Okay, and by adding sodium bromide, we're adding a common ion, an ion that is part of this KSP expression. So we're increasing the Br minus concentration. If we increase the concentration of a product, that is going to shift the equilibrium toward the reactants, which means we're going to precipitate more silver bromide, and we're going to in order to do that, we're going to use up some of the Ag+, and thereby decrease its concentration in the solution. Okay, so that was the common ion effect. The next one is the effect of pH on solubility. If the solid is the salt of, say, a basic ion, meaning the conjugate base of a weak acid, then adding acid will increase the solubility. So, for example here, calcium carbonate is sparingly soluble in water. And so we have the KSP reaction written here first, as well as as a neutralization reaction with the carbonate ion. Okay, so if we start with the KSP reaction, we see that one of the ions is carbonate. So we're focusing on the anion and imagining what if we add H's to that. So you might say, well, how do I know if it's the conjugate base of a weak acid? Well, find the anion, add some H pluses, so here that would give you H2CO3, and then consider, is that a strong acid or a weak acid? If it's not a strong acid, it's a weak acid. Okay, so if we have that conjugate base of a weak acid, then in the second reaction, neutralizing that CO3 2- with H3O+, adding acid to the solution, will cause some of the CO3 2- to become HCO-. And so that effectively decreases the concentration of a product, which will result in the equilibrium shifting toward the products. And so therefore, calcium carbonate is more soluble in more acidic water. This reaction might matter. You see I have some seashells here. Seashells are made of, among other things, calcium carbonate. That's one thing. So also limestone. And if the oceans become more acidic, due to increased carbon dioxide in the atmosphere working its way into the water, then we might find that the marine life is affected by the fact that their seashells become more soluble. So understanding this effect could have potentially global impacts. Okay, so test yourself. Which of these does not become more soluble in acidic solution? The best answer here is B, PbI2. So let's think through that. So in each case, we're looking at the anion. So we see that Cn minus could become HCN. That is a weak acid. If the I would become HI. Here, this AlOH3 would become water, and the zinc sulfide would become H2S. So for each of these, so for HCN, H2O, and H2S, these are all weak acids. And so at making a more acidic solution would decrease the concentration of the anion in these salts, the solids, which would make them more soluble. The only one that doesn't do that is HI because it forms a strong acid. Okay, the last effect we'll talk about, which is also the longest one, is the effect of the formation of a complex ion. So you read about this a couple weeks ago, but to refresh, a complex ion is formed from a metal cation, which is a Lewis acid, and a Lewis base, which is usually some kind of either an anion or something like ammonia that has a lone pair that can donate electrons. So the Lewis acid, the metal, accepts electrons, the other thing donates electrons. And so here our example is silver thiosulfate. Now this complex ion, this means that this whole thing stays together as an ion in solutions. It doesn't dissociate. So it's like a polyatomic ion, but it's got this combination of this anion and cation as well. So we define the formation of a complex ion as the reaction of the Lewis acid and the Lewis base, shown in this chemical reaction here. When the reaction is written this way, where you have the Lewis acid plus the Lewis base forms the complex ion, then this pattern, ion equals complex, the equilibrium constant for those is always given the special label Kf for formation of a complex ion. Now it should be noted that this is a different use of formation than you had in Chem 131, where you were talking about formation from elements. And we do that just to be extra confusing for you. Okay, so how will the formation of silver thiosulfate affect the solubility of AgBr? So if we allow the formation of silver thiosulfate by adding thiosulfate to a mixture of, or a solution of AgBr, then that will make the AgBr more soluble. Oops, let's go back one. It's going to make the AgBr more soluble. Okay, so let's talk about why that is. So if we have the KSP reaction for silver bromide, becomes silver plus Br minus. Okay, and then if we also have the formation of a complex ion where we have Ag plus 2 thiosulfates, then, oops, that's just 1 minus. Okay, then that's going to form a complex ion. Okay, so when we can think about these reactions happening together so that we get this net reaction of AgBr solid plus thiosulfate goes to silver thiosulfate plus Br minus. And so we can see that the formation of the complex ion effectively sort of steals silver from the KSP equilibrium. So we're removing a product from the KSP reaction, which means that the AgBr is going to become more soluble. It's going to shift toward the products. Okay, so if we have that reaction all together, what would be the equilibrium constant K for that reaction? If KSP for AgBr is 5.4 times 10 to the minus 13, and Kf for silver thiosulfate is 4.7 times 10 to the 13. Okay, so in the last slide, we had those two reactions where we had AgBr solid goes to Ag plus Br minus. And we said that was KSP. And we added to that the Kf reaction where we have Ag plus 2 S2O3 goes to Ag S2O3 2 minus, and that's Kf. Okay, we added those two reactions together to get this reaction, and when you add two reactions together, you multiply their equilibrium constants. So if we multiply KSP times Kf here, then we get an overall K for this reaction of 25.4. We can then recalculate the molar solubility of silver bromide in the presence of, say, 0.1 molar Na2S2O3. So we can use this equilibrium that we've already defined, and we said that for this K is 25.4. And our question is, what is the molar solubility, which is another way of saying what is the concentration at equilibrium. So if we want to know concentration at equilibrium, we need to use an ice table. Initial concentration of silver bromide solid. Doesn't matter, it's a solid. Initial concentration of thiosulfate, we said, is 0.1 molar. And initial concentration of the complex ion and bromide are both 0. And so then we can set up our ice table the way that we would normally. We know that the reaction has to proceed toward the products because we don't have any yet. So we get 0.1 minus 2x, x, and x. All right. So if we do all of that, and we get our K expressions, we said that K here is going to be x squared divided by 0.10 minus 2x equals 25.4. What we can do, 25.4, that's going to be squared. All right, since we have squares on both sides, we can take the square root of both sides and get that x over 0.1 minus 2x equals the square root of 25.4, which is 5.04. And if we do that, we can solve for x. So x will equal 0.504 minus 10.07x. And I get that x ends up equaling 0.046 molar. So this would be the molar solubility of AgBr in 0.1 molar sodium thiosulfate. Okay, so that's the end of our discussion of solubility. I encourage you to talk with your group on Slack, do some practice problems, and contact me with your questions.